Okay, so we're going to look at part 2 now. We're going to be looking at fast-moving projectiles and satellite motion. Now, one thing I forgot to do last time was a little juggling, okay? So what goes up must come down, and at the same speed is the basis for juggling, right? These two balls have a different mass, so they act different in my hand. But that's the idea. What goes up comes down. So that's why you can predict where the ball's going to land in your hand. Okay, now let's look at satellites. So when you've got something in orbit, that's what we call a satellite. It's moving fast enough to fall continually around the Earth. Okay, remember the idea of astronauts and stuff floating around in the International Space Station. And I said, yes, they have forces on them, but the forces help to keep them in orbit. Well, that's the idea. They are satellites of Earth, but they have to have horizontal velocity or they are going to fall down to the Earth. So when you throw a ball, it usually falls down to the Earth because you can't throw it fast enough. If you could throw it fast enough that its trajectory matched the Earth's curvature, then you could have this situation. The girl throws the ball, it goes all the way around the Earth, bonks her in the head. Okay, so when it's fast enough, it doesn't just fall straight down to the Earth or down to the Earth in a curve. It curves, but it's too fast to actually hit the surface. So Isaac Newton, again, as always, was wondering, what could happen if you shoot a cannonball very fast from the top of a high mountain? So these are his drawings. And so you can see that he thought, well, if I fire it slowly, that would be D. And if I fire it a little faster, it'll go to E. If I fire it a little faster than that, it'll go to F. And if I keep firing a little faster, it might get to G halfway around the world. How fast does the stupid thing have to be to get it all the way around? Okay, so anyway, so he was trying to predict how fast was going to make that happen. Okay, so in this book, they give you an idea of, well, what if we have a bowling alley? And the bowling alley has a gap. So the bowling alley's around the whole world. How fast does this ball have to go to cross that gap? Okay, now, one thing is that we do know that objects fall downward 5 meters in 1 second. We were just doing that. Remember that distance is 1/2 gt squared. 1/2 of 10 times 1 second squared. And that gives us 5 meters. Okay, so we get 5 meters. That's how far things fall in 1 second. Okay, so how fast do we have to send things in the horizontal velocity? So this picture illustrates a ball that was thrown at 20 meters per second in the horizontal direction. So after 1 second, it has gone 20 meters and it has fallen 5 meters. Okay, so it didn't get very far, 20 meters. So we need to throw faster, right? How fast can it go so it matches the curvature of the Earth? The Earth starts to curve away from under it. So how fast? Well, it turns out to match the curvature of the Earth, the ball has to be able to go out 8,000 meters before it falls 5 meters. Okay, that would keep it curving, following the curvature of the Earth, not falling down to the Earth, but it would parallel the surface of the Earth. So that's how fast it has to go. 8,000 meters in each second. Okay, so 8,000 meters per second, or as they sometimes say in the book, 8 kilometers per second. All right, so That's how fast. Is that fast? Yeah, it's pretty fast. It's faster than you can throw, right? People can throw it maybe 50 meters per second. This is 8,000 meters per second. Okay, so the ball has to keep going out 8 kilometers and only fall 5, and then it will match the curvature of the Earth. Okay, so when you send objects out into space, you put them on top of a big rocket so that you can go at least 8,000 meters per second. So the rocket has to go upwards and then sideways so that it can push so that it can go at least 8 kilometers per second once it gets up to the height where it wants to be. And that will keep it going around the Earth. Okay, so it's got to have that much orbital speed. Okay, now we want objects to be up above the air because that's where there's no air resistance. So that's why space shuttles and the space station are around 200 kilometers above the surface. So they're above the air. But remember, they're not above the gravitational field. In fact, you need gravity. Gravity is going to provide the centripetal force to keep it going around the Earth. So the satellite tries to escape. It's going straight, 8,000 meters per second, but the Earth, with gravity, pulls it backwards, right? So gravity is providing that centripetal force so that it keeps changing its direction, right? As we were talking about before, gravity provides that centripetal force, and that keeps the object going around the Earth. And often we put things in parabolic or elliptical orbits instead of circular ones. Those happen for various reasons, but usually we shoot them out and we give them a speed that's a little greater than 8,000. So then what happens is they go up a little too far away from the Earth, but then eventually they circle back around. And as they go up, they slow down, so they're slower up here. Then they gain speed as they come back until they're back to being their faster speed, more than 8,000. And so the shape of that is what's called an ellipse. And if you've never drawn an ellipse, it's kind of fun. You can put 2 pins and some paper, put a piece of string in it, put your pen, draw beautiful oval shape. Okay, and it turns out that parabolic paths and elliptical paths are actually related. So when you are shooting a ball or a cannonball and it falls down to the Earth, that is actually part of an elliptical path around the center of the Earth. And so eventually, if you're able to, your cannonball is able to go fast enough, then it would just circle the Earth. Right? Okay, all right. And a circle is a type of ellipse, can be one special case. Okay, so that's the end of this section.